Okay, welcome to today's video on centripetal acceleration. In today's video, we're going to derive the formula, so A equals V squared on R, and we're going to use this using a car turning a corner example. And we're going to have to use the small angle approximation. So let's have a look at this here, this diagram of a car turning left around a corner. Now I've drawn a nice little arc like that. And we're going to draw the center of the circle here from the middle there out to the position of the car in each instance. Okay, now here is theta, the angle between, or the change in angle as the car turns, and r is the radius from the center of the circle to where the position of the car is. And delta S here will be the displacement of the car, or how the change in displacement there. So the car's initial position to its final position there. Now in this example, we're going to assume a constant speed for the car. So what this will mean is the magnitude of the final velocity is the same as the magnitude of the initial velocity, so that's constant speed. And for this derivation, we need to find the change in velocity, which will be Vf minus Vi, which will give us delta V. Now we did this in the previous video to work out the change in velocity there. And there you can see that theta is also the angle between Vf and Vi, or minus Vi there, which is also the same angle theta as the green angle there when we draw up the vectors R and R, and we draw the arc as well for delta S there, which is that triangle drawn there. So those thetas are actually equal. Okay, now for this we've got an arc there for delta S and a line there for delta V, but to kind of equate this we need a small angle approximation. So what is a small angle approximation? Well, I'm going to explain this in quite a unique way. First of all, we're going to look at the Earth and we're going to take a tiny little fragment there. Now as you can see there, if that angle theta is really small, the O side of that triangle almost equals the arc, and the adjacent side is almost equal to the radius, and is almost equal to the hypotenuse. Okay, now the analogy here is at the surface of the Earth, when the angle is really small, the Earth pretty much looks flat, and that hypotenuse and the adjacent side and the radius are all pretty much the same to the center of the Earth. And that arc length, or the opposite side as well, they're also equal. Okay, so what we can actually do there is we can kind of say we know tan theta is O on A, sine theta equals O on H. And also another interesting thing, if you didn't know, that theta, or the angle in radians, is actually the arc length, divided by the radius, and in this case the radius is the adjacent. Okay, so we can actually see that all these three things are equal. So tan theta, which we'll write here, is actually approximately equal to sine theta, which is approximately equal to the theta in radians, which we'll get to writing there, which is also equal to the arc length over the radius. And for this particular example, this means, and we'll go back to our particular activity here, or derivation should I say, is that this kind of says that they're similar triangles. So that delta S, although it's an arc, it's pretty much a triangle there, and therefore the ratios are equal. So we can say they're similar triangles given that theta is really small if it turns a really small angle, so the ratios are equal. So for the first triangle, the change in velocity, or that small side over the velocity, which we know is the speed, is the same as the change in displacement over the radius. Okay, so that's the formula there. Now we're going to divide by the change in time. Okay, so both sides by the change in time. So what we're going to get with the left hand side, we'll get delta V on delta t times the speed vector or velocity vector, and that's going to equal delta s on delta t times r. So we just divided both sides by delta t, or a time interval there on both sides. Okay, now we can actually pick a few things from here. Delta s on delta t is actually the same as our velocity or speed, and delta v on delta t is actually our a vector or acceleration. Okay, so now what we've got here, simplifying this, is we've got a on v, or acceleration on velocity, is equal to the velocity on r. Okay, now that leads there to, if we multiply both sides by v, we get a equals v squared on r. Now v times v as vectors just gives us a magnitude, so we're going to leave this in terms of magnitude, and there's our answer. A equals v squared on r. Let's do an example question now. So a car turns a corner of radius 50 meters at a constant speed of 60 km per hour. And what is the acceleration? So it's a fairly straightforward example. We're just going to use this formula that I'll slowly write down here. A equals v squared on r. Now, given in this question, what we're given is v equals 60 kilometers per hour. Now, a quick way of doing this, we have to always convert to standard units, and meters per second is what we need for velocity. So the easy conversion from kilometers per hour to meters per second is dividing by 3.6, and we get 16.67 meters per second. The radius there given from the center of the circle is 50 meters to the outer circle, and so plugging this in, a equals 16.67 squared divided by 50 there. Okay, now this gives us an acceleration of 5.56 meters per second squared, which is roughly 50-60% times the acceleration due to gravity. Cool. Now let's have a look at Geogebra. Okay, so this is a little animation that I made to kind of show you the relationship between a velocity, radius, and the acceleration, centripetal acceleration. So as you can see here, a small velocity of just 3.4 and a smallish radius of 2 will give us a small acceleration vector. Now as we speed that velocity up, you can see the acceleration get a fair bit bigger, should I say. So it's a v squared relationship, so the faster we go, the acceleration goes up by that factor squared. So if we crank this velocity up to go on a 50, and then, 15 should I say, and almost up to 20, we can see that acceleration vector gets a lot bigger. Okay, whoop, speeding up to 20 meters per second, we actually get an acceleration of 200 meters per second squared. Okay, now on the other side, if it's an inverse relationship between acceleration and the radius, so the further out we get, the acceleration decreases. So it kind of makes sense. Going around a tight corner, a small radius, there's a high acceleration, and vice versa for a large radius. Now going right in there, we can see the acceleration is really large. Okay. Thanks for watching today's video. It's always much appreciated that you watch this video. I hope you understand how that formula is derived, and now you can apply a few questions relating to centripetal acceleration. As always, subscribing is sincerely appreciated, and definitely leave some comments in the comment bank below. Thank you.